Welcome back to Bug Bounty and Beyond. I'm Ujjwal, and today I'm here to show you something that should concern every security professional. What happens when AI coding assistants go rogue? Today we are diving deep into Gen AI coding assistants gone wrong. How to test AI code suggestions, expose insecure patterns, and implement proper guardrails. This isn't theoretical anymore. We are seeing real vulnerabilities in production systems every day. Here's our security journey today. We'll start with understanding the fundamentals, move through the critical vulnerabilities, examine real-world case studies including GitHub Copilot and Cursor AI attacks, explore the complete OWASP framework, and end with actionable defenses you can implement immediately. By the end of this video, you'll have a comprehensive understanding of AI coding security risks and practical solutions. Gen AI coding assistants like GitHub Copilot, Amazon Code Whisperer, and Cursor AI have revolutionized development productivity. Millions of developers now rely on these tools to generate code faster than ever before. But here's the critical security reality we need to face. These tools are optimizing for productivity, not security. They're trained on massive public repositories, including vulnerable legacy code, deprecated security practices, and plain bad implementations. When vulnerabilities get generated at AI speed across thousands of developers, manual review becomes impossible. Let me share some research that should grab every chief information security officer's attention. A comprehensive study by NYU and University of Illinois analyzed over 1,000 AI-generated programs. The results are staggering. 40 to 44% of all AI-generated code contains security vulnerabilities. Breaking this down by language, C code shows 50% vulnerability rates, Python shows 38%. We're not talking about minor issues. These are critical vulnerabilities including SQL injection, path traversal, and insecure cryptographic implementations. The threat landscape includes prompt injection attacks, model hallucinations, and legacy security risks being amplified at scale. We're already seeing real-world breaches and compliance failures. Security is no longer optional in AI-driven development workflows. To understand how to defend against these threats, we need to understand how these systems work under the hood. These tools are powered by large language models trained on billions of lines of open source code from repositories like GitHub. They suggest code based on statistical patterns, predicting what's most likely to come next, not what's most secure. The models have limited context windows, so they can't understand your full application security posture. This is exactly why we see dangerous patterns like MD5 password hashing and SQL injection vulnerabilities. These were common patterns in the training data. The models are prone to amplifying bad coding practices and security vulnerabilities that were hidden in their massive training datasets. Based on extensive research and testing, here are the primary attack vectors you need to monitor. Prompt injection attacks involve hidden instructions in documentation or comments that can hijack AI behavior. We'll see this demonstrated in our Cursor case study. Path traversal and command injection vulnerabilities appear frequently because AI assistants generate file operations without proper input validation, leading to direct file system access and command execution capabilities. Secret leakage is widespread, with 6.4% of Copilot active repositories leaking at least one secret, including API keys, database credentials, and internal URLs. There's also the growing threat of malware generation, where adversarial actors use AI assistants to create exploit code and sophisticated attack tools. The key security insight here is that we must treat every AI suggestion as potentially malicious input requiring validation. OWASP has been tracking these threats, and their analysis aligns perfectly with what we are seeing in the field. The traditional CWE mappings still apply. We see path traversal CWE22, OS command injection CWE78, and insecure password handling CWE522 appearing repeatedly in AI-generated code. But OWASP has also identified LLM-specific risks, including prompt injection, data leakage, and insecure output handling. Security gaps are amplified by poor prompt engineering, outdated training data, and the complete lack of runtime validation in most development workflows. OWASP has developed a comprehensive framework specifically for LLM applications that we need to examine. This is your essential reference guide, the official OWASP Top 10 for LLM Applications 2025. Let me walk you through each category. LLM01 prompt injection is how attackers hijack AI behavior through crafted inputs. LLM02 sensitive information disclosure covers the secret leakage problem we discussed. LLM03 supply chain addresses vulnerabilities in third-party models and libraries. LLM04 data and model poisoning involves compromising model behavior through malicious training data. LLM05 improper output handling occurs when AI-generated code becomes an injection vector itself. LLM06 excessive agency happens when LLMs are granted unchecked autonomy. LLM07 system prompt leakage is new in 2025, addressing the exposure of hidden AI instructions. LLM08 vector and embedding weaknesses is critical for RAG-based systems. LLM09 misinformation covers the generation of false but credible appearing information. LLM10 unbounded consumption addresses resource exhaustion attacks. This data comes from peer-reviewed research by NYU and University of Illinois, the gold standard for AI security analysis. Let me break down these numbers because they are staggering. Out of 1,084 generated programs, 44% contain vulnerabilities. The language breakdown shows C programs at 50% vulnerable, Python at 38%. The vulnerability distribution chart shows path traversal and command injection dominating the results. Look at this specific vulnerable code example. It's a classic buffer overflow in C, where the AI suggested a 32-character buffer for data that could be 317 characters long. We repeatedly see MD5 being used for password hashing, SQL injection in concatenated queries, and inadequate path validation in file handling operations. This research proves that manual code review is insufficient when dealing with AI generation speeds. We need automated security validation as a mandatory step. This is the copy pasta license attack, one of the most sophisticated AI attacks documented. The attack works by embedding hidden instructions in markdown comments within README files. These instructions are disguised as legitimate software licensing requirements. Exploiting social engineering principles, the AI believes it must include this license in every file it creates or edits. Here's the viral propagation mechanism. The attack self-replicates across repositories automatically. The technical execution includes malicious imports and network requests being injected into codebases. The attack achieves persistence by spreading to new repositories without detection. It evades detection because it's hidden from standard code review processes. This demonstrates that AI assistants can become attack vectors themselves, not just generators of vulnerable code. The threat landscape extends far beyond individual code vulnerabilities. We are seeing three categories of advanced threats. First, AI-generated malware, where LLMs can generate sophisticated attack code, including ransomware components, obfuscated payloads, and exploitation frameworks. The polymorphic generation capability evades signature-based detection systems. Second, systematic data exfiltration, including the Microsoft Copilot vulnerability that exposed thousands of private GitHub repositories from Fortune 500 companies. Training data leakage affects 6.4% of repositories, exposing secrets, and one incident alone discovered over 1,600 valid API tokens. Third, we have notable CVEs, including CVE 2024-48919 for Cursor AI remote code execution, and CVE 2025-54135 and CVE 2025-54136 covering the Cur execute and MC poison vulnerabilities. Attackers are using AI to scale their operations, while defenders struggle to keep up with AI-generated threats. Effective AI code security requires a multi-layered defense approach. For testing methodologies, integrate static analysis tools like CodeQL for automated vulnerability detection. Implement dynamic testing with runtime validation of AI-generated code. Conduct adversarial prompt testing through red team exercises targeting AI systems. For guardrail implementation, think of these as runtime security policies for AI interactions. Deploy input validation to sanitize prompts and context data. Implement output filtering to validate generated code before execution. Use role-based access controls to limit AI capabilities based on user privileges. Deploy real-time threat detection to monitor for anomalous AI behavior. Enterprise examples include Microsoft Prompt Shields, blocking injection attempts in Copilot, OpenAI's RLHF providing constitutional AI training for safer outputs, Anthropic's constitutional AI ensuring value-aligned model behavior, and Lasso Security offering identity-aware AI guardrails with compliance monitoring. Start with static analysis integration, then layer on runtime guardrails and monitoring. Here's your action plan for implementing AI code security in your organization. For immediate security integration, make it mandatory that every line of AI-generated code passes through security tools including CodeQL, SemGrep, or similar SAST solutions. Establish a policy that no AI code gets deployed without security validation. Deploy layered guardrails, including input sanitization and output filtering, content filtering for malicious patterns, and automated policy enforcement with comprehensive audit trails. Implement continuous testing through regular red teaming exercises against AI systems, prompt injection testing to simulate attack scenarios, and real-time monitoring for suspicious AI behavior. This is an evolving threat landscape that requires treating AI security as an ongoing program, not a one-time implementation. Stay informed, adapt continuously, and remember that your security is only as strong as your weakest AI-generated link. If you found this valuable, please like the video and subscribe to the channel for more cutting-edge security research. Drop your questions and AI security experiences in the comments. I read everyone and create follow-up content based on your feedback. Remember to hit that notification bell for our upcoming content on advanced AI security topics. Thanks for watching. Stay secure.